Hello, everybody. Final subtopic in topic 14 is continuation of 14.3, lifting assessment methods. This is the big one. So 14.4, or lifting assessment methods part 2, is all about the NIOSH lifting equation. Now, we've talked about NIOSH before, the National Institute for Occupational Safety and Health. This is a research organization. It's interested in workplace safety for the betterment of humankind and eventually for economy and et cetera. It's not a law enforcement. It's not a legal, organization like OSHA, the Occupational, Safety and Health Administration. I forget, OSHA. OSHA are the ones that get you and can legally, require certain changes. NIOSH is a little bit more like, if you want to keep your workers happy, healthy, and effective, here's the research that can do that, that can guide that. So we have an equation. Now, in the previous 14.3, it was primarily table-based estimates of lifting, allowable or acceptable weight limits. NIOSH lifting guide is more calculating, okay? And it takes into account the major aspects that make a lift difficult and or risky, and has basically weighting factors that are derived from those factors. So we have to start with a number of assumptions. And by the way, just like with the Liberty Mutual tables, I've got the NIOSH lifting guide on Canvas. By all means, you can read it and get the details on this. I'm just going to go through the method rapidly. So first of all, we have some assumptions before we can use this method. We have to expect, an easygoing single lift, that's being the focus of our analysis here. There aren't any unexpected things in the environment that might mess with the motor control for this controlled movement. We're doing a two-handed lift. We're not having to move around anything. It's free space. Other things that I'm doing are not significantly more consuming of my energy than the lifting task. We have friction, so I'm not walking on ice, which does change the gait and change the way that I would perform lifts. It's all human powered, so no mechanical aids. We're assuming these lifts are between 2 and 4 seconds for those moves. We hope that the movement is smooth and continuous, and our inter-hand distance, hand to hand, is within 25 inches. What is that about here? Or 65 centimeters. So once we start going out further than that, it dramatically changes the biomechanics involved in the lift, and this equation or this guide doesn't really predict that very well. So as long as we can meet these assumptions, and generally if I give you a problem and say, hey, solve it with the NIOSH lifting guide, you can make these assumptions. Okay, so again, this is one big equation, and what the NIOSH lifting guide doesn't give us, the acronyms here come from NIOSH, but now we've got a whole bunch of additional letters to deal with. So the recommended weight limit is what we're solving for with this equation. Again, NIOSH doesn't have a badge to come and force any changes, so these are just recommended. This is just a way to assess, here's what we're currently asking our workers to do or might ask our workers to do, and we can get a sense for the risk level as far as injury, workplace effectiveness, etc. So we're calculating this RWL, and we have all of these factors that go into one multiplication. And essentially what this is the LC is always starting with the same value, 51 pounds. That's our load constant. So we're saying across all human workers, assuming they're adults and making all of these assumptions as well, then we start with 51 pounds. If it is absolutely ideal in every other aspect of the lift, 51 pounds is an acceptable weight limit. But basically we start at 51 pounds, and then we have all these multipliers that reduce from 51 pounds. So all of these multipliers are values between 0 and 1. And we're going to go over each of these. So there are 6 multipliers, I guess 7 if you include the load constant. But let's go through. So the most complicated one actually is the first one, I think. So the horizontal multiplier. This accounts for the fact that the further away from my torso I am holding a load, the more effort, the more energy, the more force, the more torque on my back, the more difficult the lift, basically. So we want to essentially reduce that recommended weight limit as you move further away from the torso. And so that the dimension H, pointed right here, is what we're interested in. This 10, this stands for 10 inches. I forgot the inches there. I guess I put it right there. But if it's in inches, make sure you're using this equation. I think I've got an example. Yes, there could be metric system. Let me get to that on the next slide. But yes, this is what we're solving. We want to know H from the center line of the body, the center of mass in this dimension, in this vertical plane, to the center of mass of the load, and it's usually halfway the depth of that load, right? So yes, here's a little more of a more precise view of H. You'd find the midpoint between the two ankle bones when somebody is standing in balance. That would represent the vertical axis midpoint. And how far out do we go? All right. So H is the big thing we usually have to either measure for or approximate. And this, this weighting factor, the horizontal multiplier, accepts values between 10 inches and 25 inches as far as that direction outward from the center line of the body. If it's less than 10 inches, the assumption is this is running into the belly. It's going interior to the body. So of course we're making an assumption with that 10 inches. We're making an anthropometric generalization, but this NIOSH equation is supposed to account for all human workers, so it's a pretty big approximation. But yes, so if we give a value less than 10 inches for this H, or if you calculate H and it ends up being less than 10 inches, use 10 inches. 10 inches should be your minimum value. Shouldn't be less than that for H. And if it's greater than 25, we say, well, this is beyond our reach. This is not an effective stance or really reasonable way to perform a lift. So we say lifting doesn't occur beyond 25 inches. Yes, here's that note I wanted to get to. I'm giving you all the multipliers in the English system, inches and pounds. If you're going to use the metric system, centimeters and kilograms, just make sure you're carefully looking at, which system you're using for these equations. Now, I'm giving you all the ones for inches. I know that you can convert those to centimeters, 2.54 centimeters equals 1 inch, but there are also in the textbook tables that have the metric, the metric values if you want to look at them that way. Okay, so we're still calculating here this horizontal multiplier, the most complicated one. If you are given, two different right-hand positions, maybe I'm gripping it in a strange way, you look at the average between those two. So H equals, sum of the two divided by 2. And then if we can't measure it directly for whatever reason, then we have this approximation for including the torso. Okay, so basically we go like this. So first we have to say, are we lifting from the ground, and less than, are we lifting total distances or the vertical location from less than 10 inches? And if so, we want to use 10 inches plus W over 2. So this is accounting for a little bit more bending over, having a little more horizontal distancing there. If the V, being again the vertical location, is greater than 10 inches, then we can use 8 plus W over 2. And again, I should have put inches here. Sorry, these are 10 inches, 8 inches plus W over 2, W given in inches. W, now this is a little confusing. So ring, this is a good thing to pay extra attention to. W in this equation stands for the depth. So W, we normally think of the width. Well, width in this case is the width in the horizontal dimension. So it's really the depth away from me. So if I've got this box and it is 20 inches deep, then my W is 20 and halfway of W is 10 inches. That's where I'm grabbing it halfway, halfway up that to the center of mass of that box. And then I'm adding 8 or 10 inches based on my belly. So if I'm standing upright, you know, it's a little closer to my body. If I'm bent over way down near the ground, it's a little bit further out. Okay, so again, those are our approximations that you can use for homework, for exams, etc. These guys right here. And typically H is the complicated thing to calculate. All right, so vertical multiplier. Now this is the next one. So 2 of 6 here, multipliers. So here's the equation for this one. Basically, this accounts for the ideal height of 30 inches. So again, this is an anthropometric big time average across all adult workers. But they say 30 inches is our ideal vertical height. And I'm either going above 30 inches and that costs me a little bit more, or I'm going below 30 inches and that costs me a little bit more. So we have an absolute value here of V being the vertical location. Subtract 30 inches to see how far away from 30 inches it is. Now, if I'm above or below 30 inches, I have the same effect on this multiplier, right? So again, 30 inches, and it gets worse if I go up or down. Now, the reason that matters is because when you do problems, you're going to have to look at the starting point and the ending point of a lift or load, right? Starting point and ending point. And you want to find the value of the vertical multiplier, which is smaller, the minimum value of the vertical multiplier from the starting point and from the ending point, the minimum of those two, okay? I'll show you this in an example, but don't forget that, very commonly forgotten to look at both the starting point and the end point. Which one of those is smaller? Don't use both of them. You find out which one is a smaller number and therefore a more reducing multiplier. And you're going to use that one in the weightings equation. Okay, so again, V, that's my height. Starting or ending point, I want to know, those are the two extremes of my lift. And so I'm going to look at both of those and subtract 30, take the absolute value, multiply by 0.0075, subtract that from 1. All right, so from 0 to 70 inches, this is the range of acceptable, I suppose, lifts. You'll notice, I bet if you put 70 in here and multiply this out, you'll end up with a vertical multiplier of 0. So that's how that works out mathematically. Yes, and this note, just start one more time, make sure you do both the origin and the destination and only take the smaller of those two values. And you'll see when we go through our example here coming up. Okay, next one, distance multiplier, dm. This one's a little more straightforward. D is the total vertical distance, V start and to V end, whatever that is in an absolute value sense. And then you divide 1.8 by that absolute value there. I should have absolute, this is an absolute value, shouldn't have a negative number here ever. And then there you go, the distance multiplier becomes a value between 0 and 1. And 10 inches is the minimum for this. And you'll note if D is 10 inches, then this becomes 0.82 plus 0.18, which equals exactly 1.0. So it can't be higher than that number. Therefore, the minimum D is 10 inches. So if I'm only moving it 6 inches up, I want to see in your equation, you still use 10 for the D value in this equation. Asymmetry, this is where we finally get to look at the fact that pivoting is really problematic. And so this is the equation that handles that. 1 minus 0.0032 times A. A is the amount of pivot in degrees. So 0 to 360 degrees, or I'm sorry, I guess from 0 to 135 is the acceptable range there for this multiplier. And frequency multiplier, the more I perform a lift per unit time, the less that overall weight should be. The range of possible lifting frequencies that can be handled by this equation are 1 in every 5 minutes, or basically 0.2 lifts per minute, all the way up to 15 lifts or more per minute. Typically, we're talking about how many lifts per minute, not how many minutes per lift. But you know, sometimes it's easier to talk either way. Also need to think, are we talking about an 8-hour shift? Are we talking about a 12-hour shift? Are we talking about hey, I just need you for 30 minutes to do this really hard work once in the day? each of those matter, as far as how much we can handle. Now, this is the only one, like the Liberty Mutual tables, everything is looking it up in the right column and row of the table. Frequency multiplier, this is the only one where, well, I guess technically there's one more, where there's a table lookup value. But certainly for frequency, come to this table, and this is in the textbook. This is the version I've got here is from the previous version of the textbook. That's why it's table 11.2. I would guess in the current textbook, it's like 13 or 14.2, whichever the chapter is that goes with this, 13.2, 13 point something, it would be in the textbook. But I do want to definitely point out, if you're going to use this table, which you certainly can, I guess I'd recommend it for your homework and things to come to this table. But recognize that this table gives everything in centimeters. So all the equations I've been giving you, I'm inches, 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 and then thanks a lot book, they go and they mix it up on us. So I just wanted to point that out. If you use the same multipliers and just assume this is 30 inches, then you can interpret these all the same. So 1 hour less than 30 inches or greater than 30 inches, up to 2 hours less than or greater than 30 inches, and a full eight hour shift less than or greater than 30 inches. And so it's basically just a lookup here. We have we determine what's the overall work duration, what's the nature of, where is the vertical point, is it above or below 30 inches, and then how many per minute. And that's how we basically find what we need. All right, last one, last multiplier, at least the coupling multiplier. It handles the fact that if we don't have good grips, if I don't have handles, for example, and I have to just palm it, there's considerably more force that has to be applied without a good solid grip. So we have these multipliers. This is a very subjective sort of, is that a good coupling or medium or poor? Generally, I'll just tell you for the homework or for the exam, I'd say, Dr. F says this is a fair coupling. So you would just then come to this table, see that, all right, are we less than or greater than 30 inches? Again, let me just remind you again, 75 centimeters is 30 inches, or within a, close enough. So that we're talking about the same 30 inch sweet spot above or below that for all of these things involving V. Okay. If we've got good handles, great. Then there's no further, reduction of in our weighting scheme. If they're not great, we are going to reduce, up to, 10%. All right, there it is. So coming back to our big math equation, recommended weight load constant by horizontal multiplier, by vertical multiplier, by distance multiplier, by asymmetry multiplier, by frequency multiplier, by coupling multiplier. All right, so once we calculate all of that, now we have something that can be meaningful in terms of making decisions, for our work system. So, I know NIOSH can't come and arrest us for having people, lift something that's pretty heavy, but how happy are they going to be? And when do we need to start thinking, we're going to start losing workers due to injury, due to, they're going to quit. And therefore, maybe it makes sense to start investing in some engineering solutions that aren't just more, more burden on the human. So we have the lifting index, and it's essentially a multiple of the recommended weight limit. It's a multiple of that according to what is actually being lifted. So if our recommended weight limit is 10 pounds, and the actual lifted weight is 20, well, we say, yeah, it's above the recommended weight limit, but it's a lifting index of 2. It's double the recommended weight limit. And the multiples of that limit are what kind of drive the recommendations here. So if everything is at 1, everything's relatively okay. You get to 2, this is where workers start to complain. And at 3, this is where, you really, at least as a rule of thumb, it makes the most sense to make engineering solutions, come into play, because you have high risk of injury or problems with your workers. And you might, come up with all of these lifts that have to get done in a day. We can prioritize maybe which ones are the most problematic by the lifting index. All right, so I hope you remember our example from 14.3. It's the same numbers, same problem here, same antique TV chassis manufacturer that looks like this. All right, so how would we then solve this using the NIOSH equation? So first thing, we want the recommended weight limit. We remember that sorry, that's an animation issue. The load constant is 51 pounds. It's always 51 pounds. Always going to start with that. If it's kilograms, make sure you get the right load constant. So our horizontal multiplier, 10 inches divided by H. And we are going to use this approximation for H because we don't really know exactly how they're holding it. We can sort of approximate, but we know since we're not given the ability to directly measure this, we're going to use one of these two approximations. We are saying, they're 3 feet off the floor, they're standing 2 feet. So we're above 10 inches. That was the main distinction for this approximation. Therefore, we use this version. Actually, let me just go back to that to make sure. So right here, this one right here, H can't be measured directly in this case. So we're going to use this one because our vertical position is greater than 10 inches. It's not down by our feet. All right. Sorry. Oops, getting ahead of myself. Okay, here we go. All right, so plugging those in, we know W because we know the depth of our chassis here, 26 inches deep. And so we also have to remember there's this additional gap of 3 inches that we have to reach over according to the problem statement. So we're going to put all those together. The H distance is 8 inches. That comes from this approximation from my gut, basically from my torso, plus halfway down the depth of this chassis, so 26 inches divided by 2, plus 3 more inches to get over this gap. Okay, so the total H here, when I'm supporting the weight of these chassis, is 24 inches. This is right out near the edge of what was an acceptable range, if you remember. All right, good. So yes, animation, sorry. So plugging those in, this is our horizontal multiplier. We've now solved for that multiplier, 0.42. Okay. Vertical multiplier. Remember, again, we need to look at the origin and the destination. Okay. It turns out I'm going from 36 inches high, the 3-foot tall conveyor, to the 24-inch high stand that's next to me. So I've got 36 inches, I've got 24 inches. Turns out both of these give me the same multiplier, the same ultimate calculated value. I'm still going to look at the minimum of those two. It just happens that they're both the same value. So I know my vertical multiplier will be 0.96 in this case. There you go. Minimum of those two equals 0.96. All right. So we've got load constant and then horizontal multiplier and vertical multiplier. Our distance multiplier, we're going from 3 feet to 2 feet. So that's 12 inches. There we go. 12 inches goes right there. Remember, this value should not be smaller than 10 inches. So if the distance that you're lifting is less than 10 inches, make sure it's a 10 there. All right, so there we go. There's our multiplier. Our asymmetry, I'm pivoting 90 degrees, you might remember. So plug that in. And there we go. I get 0.71. Our frequency multiplier. So we know our vertical height is somewhere 24 or 36, right? Above or below 30 inches. It could be either of those. We got 6 lifts a minute and an 8-hour shift. So here we go, 8-hour shift. I'm going to look at both the below 30 inches and the above 30 inches. I've got both of these, and I've got 6 lifts per minute. That's how I got to this point in the table. I noticed these are both the same value. Phew, now I don't have to worry. But if I had one that was smaller than the other, I would use the smaller of the two. Okay, so there you go. It's again to be more conservative in that case. All right, so if I look at the picture of the guy trying to grip this giant PV chassis, I'm going to say, Ferris is going to say, that's a poor coupling multiplier. So again, you're just getting that from me. But the reason it's poor is because there's essentially no hand grips, hard to grab, your slippery material, awkward posture. So yeah, we're going to use poor, and therefore it doesn't matter less than or greater than 30, we're going to use 0.9. Now, if this, if I had said the coupling multiplier is fair, and you look at this and you say, okay, well, I've got V below and above 30 inches. Remember, above 30 to start, below 30 at the end of the lift, at the lower, I guess. So I'm again going to look at both of these and take the smaller of the two. So basically, yeah, if I'm going down below 36 inches, or sorry, 30 inches, which I am, I'm going to use the smaller value if the coupling was fair. In this case, it's poor, so boom, there you go, 0.9 for both. And then I just simply do the multiplication, and you'll notice 51 pounds very quickly gets reduced down to a very small number. So this is very representative of what you might calculate in terms of a recommended weight limit. I'm going to definitely have you do an example of this in your homework. So, you know, this is sort of a reasonable value. You know, it's going to be less than 51. It's not going to be, you know, you know about what 3 pounds feels like probably, and you can kind of say, yeah, I can imagine if I had to do that all day, that's a reasonable weight limit. But if I did this 6 hours a day at the number of lifts that are, you know, required with this frequency, I'm doing quite a bit more. I'm exerting that much more energy. 3.7 tons a day makes it, you know, really puts it in perspective. All right, so again, lifting index. Now we know our recommended weight limit. And we want to know, you know, okay, increased risk of injury once we get above a 1. If we get to 3, we're really in trouble. And this, you know, and whichever lifts are the higher lifting indexes, they're going to be more problematic. They're going to be the ones that you want to redesign first. So if we have with our, you know, squat boxer, if this is 8.5 pounds, the lifting index is the actual weight, 8.5 divided by the recommended weight limit, 3.4. Our lifting index is 2.5. 2.5 is getting close to 3. You're going to have some complaints, but potentially you're going to have just really, really hard work without people, you know, reaching that potential threshold of injury point. All right, so that's it. Solving for the recommended weight limit and the lifting index. That sort of comprises how you would use this NIOSH lifting guide. And that is it for topic 14. Thanks, everybody.